Hello, everybody, and welcome to this week's lesson. So this week we're going to be continuing our work with two-dimensional geometry that is flat shapes or plane figures. We're going to be focusing this week on triangles and using the Pythagorean theorem. So that phrase might sound familiar to you, or it might not. That's okay. We're going to work on it together. So our learning goals for this week is that by the end of this week, you will be able to use the Pythagorean theorem to determine unknown side lengths in a right triangle, do calculations involving exponents and square roots, and use the Pythagorean theorem to find the distance between 2 points. So the materials you're going to need for our lesson today is pencil and paper, of course. You always need those when you're doing math, right? You'll also be using a calculator. You need your GED math formula sheet, and you might also find it helpful to have your previous geometry lesson notes in front of you, because like I said, we're going to be building on that two-dimensional geometry that we started back in May and June. And we're going to start with a little warm-up problem today. If you have reviewed those previous geometry lessons, this problem might look familiar to you because I just grabbed it straight out of one of those lessons. So it says, Eva has enough mulch to cover 100 square feet of a garden. She wants to make a rectangular garden that is 25 feet long. What should be the width of her garden? And then I've got a little picture there for you as well. So I would pause the video here and give this a try, and then when you're ready, start the video back up and we will go through it together. Okay, so Eva has enough mulch to cover 100 square feet of a garden. If you think about what mulch is doing, mulch is covering an amount of space, right? It's covering flat ground. So that idea is related to our measurement of area that we've been working on these past few weeks. So that 100 square feet is a measurement of area. You might also know that because it's in square units, right? Anytime we say something like square feet or square inches or square miles, square kilometers, anything like that, we're talking about area. So Eva's garden should have an area of 100 square feet so that she has enough mulch. We can start with that. The area of the garden should be 100 square feet. We know that. And then we have the second piece of information. So she wants her garden to be 25 feet long. Maybe that's like the length of her yard or something. So the area needs to be 100 square feet, and then it's going to be 25 feet long. We need to figure out the width. So what should be the width of her garden so that it has an area of 100 square feet? So to figure that out, we need to think about what goes into the area of a rectangle, or how do we calculate the area of a rectangle? This is where your formula sheet comes in, or maybe you have this formula memorized by now. So we know that the area of a rectangle is equal to the length times the width. The length times the width. So let's fill in the information that we know here. So we know the area. I'm going to replace the area with 100. And we know the length of this garden. The length is 25 feet. Our missing piece of information here is the width. So we're saying that 25 times something equals 100. You might be able to figure that out off the top of your head. You might know that 25 times 4 equals 100. But if you're not sure, you could do a little division to figure it out. So if 25 times something equals 100, then that something is going to equal 100 divided by 25. And 100 divided by 25 is 4 feet. So the width of her garden should be 4 feet. So she's got kind of a long, skinny garden. 4 feet. Okay. So the purpose of that was just to get you back into thinking about these geometry formulas, thinking about measurements like feet and square feet, all that stuff, just to brush off those cobwebs since it's been a few weeks. Okay. So like I said, our ultimate goal today is to be able to use what's called the Pythagorean theorem to help us with some geometry problems. First, we're going to get some practice with calculating exponents and square roots because those are involved in the formula that we're going to be using. So again, this might be something you've had some practice with before, or you might not really have seen it much before. That's okay. We're going to go through the basics together. So exponents and roots are just another pair of operations. Operations are the things that we do with numbers. So the first pair of operations that we're familiar with is addition and subtraction. Those kind of go together. And then we're also familiar with multiplication and division, multiplication and division, those go together. And so now we have exponents and roots. So an exponent is something that shows repeated multiplication. That's what an exponent does. And I have some examples on the screen here for you. So the exponent is this little number up above the main number here. So these little numbers are the exponents. You might also see an exponent called a power, sometimes called a power, or you might see it called an index sometimes. That's a little bit less common, but the most common names are either exponent or power. The big number, so the main number, is called the base. So the big number is the base. And then the little number that's up above is the exponent, also sometimes called the power. And so the exponent tells you how many times the number is multiplied by itself. So I start with this example of 4 to the power of 1. So 4 to the power of 1, that means we just have 1 4. We don't even get the chance to do any multiplication. It's just 1 4 all by itself. So 4 to the power of 1 is actually just the same thing as 4. The next line here, we've got 4 to the power of 2, or 4 to the second power. You could say it either way. And that means we have 2 4s now. So 2 4s that we're multiplying together, which gives us 16, right? We know that 4 times 4 equals 16. Okay, and then the next line here, we have 4 to the third power, or 4 to the power of 3. And that's 3 4s multiplied together. So 4 times 4, we know 4 times 4 is 16. And then 16 times 4 is equal to 64. And then we could put one more 4 in the mix there. So if we have 4 to the fourth power, or 4 to the power of 4, that means 4 4s multiplied together. 4 times 4 times 4 times 4. We know 4 times 4 is 16. 16 times 4 is 64. And then 64 times 4 is 256. So you can see our numbers are getting very big very quickly here. One note I want to make about vocabulary here, about this 4 to the second power here, or 4 to the power of 2. This exponent is very common, and it's actually the exponent that we're going to be using a lot later on in the lesson. And we have another kind of shorter term that we use for it. Instead of saying to the power of 2 or to the second power, sometimes we'll just say squared. So another way that you could say this 4 to the power of 2 is you could say 4 squared. and it means the same thing. It means 4 to the power of 2. I would avoid developing the habit of saying 4, 2. If you say that, I might be able to figure out what you're saying if we're both looking at the same thing, but if not, it might be a little confusing. So you want to make sure you're not just reading the numbers that you're seeing on the page, but that you're trying to use those correct vocabulary words. So to say this right here, you've got a few options. You could say 4 to the power of 2, 4 to the second power, or the shortest way to say it is 4 squared. All right, so we're going to get some practice calculating or evaluating exponents on this page. So again, you can pause the video, take a few minutes to calculate these, and then when you're ready, come back and we'll go through them together. All right, so this first one here, it says 5 squared, or 5 to the second power. So that means 5 times 5, which is equal to 25. All right, and then the second one here, we have 1 squared. That means 1 times 1, which is equal to 1. And then next we have 3 squared, which means 3 times 3, which is equal to 9. Next one we have here at the top of the second column is 2 squared, which is 2 2's multiplied together, 2 times 2, which is 4. And then the next one here, we have 2 to the power of 3. So 2 times 2 times 2. We know 2 times 2 is 4, and then 4 times 2 is 8. And then finally here we have 3 to the 5th power, 3 to the power of 5. So that is 5 3's multiplied together, 3 times 3 times 3 times 3 times 3. Now you could do this by hand for sure, right? You'd say 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is something. You could do that multiplication and then times 3. I'm gonna bust out my calculator to do that calculation a little more quickly. So I get 3 to the power of 5 is 243. Now most calculators, even basic calculators, can deal with exponents and roots. So if you have a calculator that you're working with and you're not sure of how to calculate exponents and roots on it, get in touch with me and we can take a look at it together. You might be using this calculator here, or you might be using one on your phone or a different calculator. Doesn't matter, most of them can do it. So if you need help with that, definitely get in touch with me. All right. Now we're gonna go on to roots. So roots are the inverse or the opposite of exponents. I mentioned before that our operations come in pairs. So addition and subtraction are inverses of each other. And then we have multiplication and division, which are also inverses of each other. And so now we have exponents and roots, which are inverses of each other. So we're going to be focusing today on square roots. This is the root that kind of goes along with squaring something. So just like you can have an exponent of like 5, you can also have a 5th root. That's totally okay. You can do that calculation on your calculator, not a problem. It's just not very common. It doesn't come up very much, and it's not relevant to the Pythagorean theorem, so we're not going to focus on it today. If you do want a little more info about it, let me know, and we can chat about it for sure. So we're going to focus on square roots. Like I said, a square root is the opposite of squaring something. So if we start with this example here, 4 squared is equal to 16. That means that the square root, so that's what this symbol here means. It means the square root of 16 is 4. So when I ask you to calculate the square root of something, of a number, I'm asking you what number times itself equals the number in the question. So what number times itself equals 16? What number squared equals 16? That is what we're asking ourselves when we're trying to figure out the square root of 16. So in the case of 16, the answer to that is 4. Another piece of vocabulary here, you might hear the term perfect square. A perfect square just means a number whose square root is a whole number. So when we ask ourselves the question of what number squared equals 16, right, the answer to that is a whole number. The answer is 4. So 16 is an example of a perfect square. But what if we just move one number up? What if we go to 17? Can you think of a whole number squared that equals 17? Well, we know that 4 squared equals 16. 5 squared equals 25. So we just jumped up to 25. So the square root of 16 is actually going to be in between 4 and 5. It's going to be a decimal number. And if I bust out my calculator here, square root of 17. So I get this nice long decimal number. It's just a little bit over 4. So it's 4.123105626. Goes on for a while there. But it's not a whole number. So 17 is an example of something that is not a perfect square. So 17 is an example of a number that you would need a calculator to calculate the square root of. Certainly on the GED test, they wouldn't expect you to figure out that answer without a calculator. But it is perfectly reasonable that they would expect you to be able to do the square root of 16 without a calculator. Because really all you need to know for that is you need to know your basic times tables. So if you don't know your basic times tables, you should be practicing them. Okay. So let's take a look here at the next page. We're going to get some practice with evaluating or calculating some square roots. So in the first column here, it says evaluate without a calculator. So these numbers here in the first column are all examples of perfect squares that we just talked about. Because their square roots are going to be whole numbers, you should be able to figure it out just by being familiar with your basic times table. And then in the second column, you can evaluate with a calculator. And I'm asking you to round to the nearest hundredth, because you're probably going to get a whole long string of decimal numbers for each of these. I don't need to know all of them. I just want to know to the nearest hundredth. So take a moment to pause the video and give each of these calculations a try, and then come back when you're ready and we'll go through it together. Okay, so square root of 1. What number squared equals 1? Well, that's going to be 1. Square root of 4. What number squared equals 4? Well, that's 2. Square root of 9. What number squared equals 9? Well, that's 3. Square root of 25. What number squared equals 25? So what number times itself equals 25? And that's 5. And then we've got square root of 100. So what number squared equals 100? What number times itself equals 100? And that's going to be 10. So again, those problems should be not too difficult if you know your times table really well. If you don't know your times table really well, you're gonna be struggling a little bit. All right, let's move on to the second column here. So now we can bust out our calculators. We want, for the first one, we want the square root of 5. So I'm getting 2.236067978. I don't need all those. I just need it rounded to the nearest hundredth. So if I have 2.236, well, this 3 is the number sitting in the hundredths place. I look to the number to the right of it. It's a 6. That tells me to round the 3 up. So my final answer here, rounded to the nearest hundredth, would be 2.24. All right, next one, square root of 6. Now I would predict that this number is just going to be a tiny bit bigger than the square root of 5, right? Because 6 is just a little bit bigger than 5. And it looks like that's right. So I, on my calculator, have 2.449. I'm getting 2.449. That's going to round to 2.45 when I round to the nearest hundredth. Okay, next one, we have the square root of 20. So let's think about this here. We know that the square root of 16 is 4. The square root of 25 is 5. So again, the square root of 20 is going to be somewhere in between 4 and 5. It's going to be a decimal number. So square root 20, I get 4.472. 4.472. So if I round that to the nearest hundredth, it's going to be 4. Oops, getting ahead of myself here. Erase that. 4.47. 4.472 will round to 4.47. All right, square root of 32. I get 5.656. 5.656 will round to 5.66. By the way, if you guys ever watching these videos and you catch me making a mistake, please let me know. I make mistakes, it definitely happens, and I don't want to record them and put them up on the internet for everyone to watch. So let me know if there's a mistake in here so I can go back and fix it. I will always greatly appreciate that feedback. All right, and then finally we've got square root of 90. 9.486, so that's going to round to 9.49. Okay. Now we're finally onto the geometry, huh? So when we talk about the Pythagorean theorem, we are talking specifically about right triangles. So everything we discuss with regards to the Pythagorean theorem is all talking about right triangles. So we know what a triangle is, right? A triangle is a shape. It's a flat shape that has 3 sides and 3 angles. So 3 sides and 3 angles. Remember, angles means the corner. So an angle is where 2 lines meet and make a little corner. So for all triangles, the angles always sum to 180 degrees. So it doesn't matter what triangle you're looking at. You could be looking at a triangle in your bedroom. You could be looking at a triangle on Jupiter. Doesn't matter. The angles always sum to 180 degrees. And then a right triangle is just a specific type of triangle. It's a triangle that has a right angle inside of it. And if you remember from your geometry vocabulary list, a right angle is a 90-degree angle. So it's when you get that nice square corner. And so I've got an example here on the screen. This is a triangle, and specifically it's a right triangle. We might know that just from looking at it, it looks like a nice square corner, but then we also have this symbol here, this little like red square in the corner. And that little symbol also tells us that this is a right angle or a 90-degree angle. So a right triangle is a triangle with a right angle inside of it. And then we have some vocabulary words, some terminology for the three different sides of a right triangle. So we sometimes call the two shorter sides the legs. So those are the two sides that are touching the right angle. In the picture on the screen here, that would be sides A and B. And then we call the longest side the side that's across or opposite the right angle. We call that the hypotenuse, which I think is a very fun name. You might also sometimes see it spelled with one more E. So sometimes spelled hypotenuse with an extra E in there. Pronounced the same way either way, hypotenuse. So the hypotenuse is the longest side of a right triangle. It's the side that is opposite from the right angle. All right, so finally we get to the good stuff. We get to the Pythagorean theorem. So in a right triangle, the legs, the two shorter sides, and the hypotenuse, the longer side, always have the same relationship to one another. And that relation is described by the Pythagorean theorem. So when we say theorem, we just mean a mathematical fact. So it's a true statement that we can prove using mathematical concepts. Now, I'm not going to go into the proof of this theorem in this lesson. It's not really relevant in terms of preparing for the GED test, but if you are interested in how mathematicians figured this out or how we show that it's true, let me know and we can chat about it a little bit more. So the Pythagorean theorem, like I said, it describes the relationship between the three sides of a right triangle. And what it says is that the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. So the sum of the squares of the legs is equal to the square of the hypotenuse. So that's true for every single right triangle in the whole universe. Doesn't matter if you draw a right triangle or I draw a right triangle or your Aunt Peggy draws a right triangle. All of us are going to have right triangles that follow this relationship. And so we can state the Pythagorean theorem with this description with words, or we can wrap it up in a nice little package, which is this equation here. So this equation is just a shorter way of making that statement about the relationship. So if we think of the two legs as being A and B and the hypotenuse as being C, then we can say that the sum of the squares of the two legs, so A squared plus B squared, is equal to the square of the hypotenuse, so is equal to C squared. And that's kind of the famous equation. Again, you may have heard that equation before, A squared plus B squared equals C squared. Oftentimes it's something that you'll learn in high school math. Okay, so let's take a look at an example where we actually use this equation or this formula. Oh, I think I forgot to mention that this formula comes right off of your GED formula sheet. So I just took a little screenshot here of the GED math formula sheet. You will find it towards the bottom of the formula sheet. It says Pythagorean theorem, and then it says A squared plus B squared equals C squared. So you don't have to remember this equation, or if you're taking a test and you forget it, you can always look back at your formula sheet. Okay, so it says determine the length of side C for the given triangle. So I look at this triangle and it looks like a right triangle. I've got this nice right angle here. And I know the two legs. So I know the length of the two shorter sides of the triangle. And so I know that I can use the Pythagorean theorem to solve for this missing side length. So I'm gonna copy down my formula. It's always good to do that as your first step. Just copy it down, get it on the paper in front of you. So a squared plus b squared equals c squared. And now I'm going to start filling in the information I know. With a squared and b squared, so those are the two legs. It doesn't really matter which one you say is which, as long as it's the two legs, the two shorter sides of the triangle. So let's say a is 3 feet. So we have 3 feet squared plus 4 feet squared. And that equals our hypotenuse squared. Okay, so now I'm going to start simplifying this side of the equation. So I'm going to start doing these calculations as much as I can, following the order of operations. So I'll do my exponents first. So 3 squared is equal to 9. And 4 squared is equal to 16. So now we know that 9 plus 16 equals c squared. And then 9 plus 16, that's equal to 25. So we know 25 is equal to c squared. Now, are we done? Did we figure out the length of side C? No. All we have so far is we figured out what c squared is equal to, but we don't want to know c squared, we want to know c. So our final step here is going to be to take the square root of 25. Because if some number squared equals 25, that means that that number is the square root of 25. So c is going to be the square root of 25. That means c is equal to 5 feet. And we're done. So in general, if you have a problem involving a right triangle, probably what it's going to be asking you to do is solve for one of the sides, and you're going to be told 2 of the sides. So you're going to know 2 of the sides, and you're going to be solving for the one missing side. And that process is going to be really similar to what we did here. So you copy down your formula, fill in the information you know. You simplify the calculations. So here we squared the numbers, added them together, and then the final step was taking that square root. And that's always going to be the final step when we are using this Pythagorean theorem formula. All right, let's take a look at a couple more examples here. So again, what I'd like you to do, I'd like you to pause the video here, give each of these problems a try, take your time with them. You may use your calculator, and then when you've given each of them a try, come back to the video and we'll go through them together. Make sure you read the directions carefully. Okay. So it says, find the missing side length for each right triangle. Round your answers to the nearest tenth. So we know we're going to be rounding to the nearest tenth. Let's start with number 1 here. So with number 1, I look at this right triangle and I can see that they've told me the 2 legs. They've told me what the 2 legs are, and I'm looking for the hypotenuse. I'm looking for the longest side. So I'm going to jump right into my formula here. I'm going to fill in the information I know. So I know my 2 legs, got 4 squared plus 6.5 squared. And that's going to equal my missing side squared, my missing hypotenuse squared. In this problem, it's labeled as x, so x squared. Okay, then same process as before. So 4 squared equals 16 plus 6.5 squared, which equals 42.25. And that equals x squared, right? Our unknown number squared. Okay, now I'm going to go ahead and add those together. So 16 plus 42.25, I get 58.25. Equals my missing hypotenuse squared. Okay, so we're getting pretty close here. Now our final step is to take the square root because we don't want to know x squared, we want to know x. So x is equal to the square root of 58.25 use my calculator for that. So I get 7.632, and then it goes on past that. So 7.632. The directions tell me to round to the nearest tenth. So 7.632 to the nearest tenth, that's going to be 7.6. So x is equal to 7.6 centimeters. All right, let's try number 2. Number 2 is a very similar situation. We are told the two shorter sides, the two legs, and we are solving for the hypotenuse, the longer side. So I'm going to use the same process here. 10 squared plus 15 squared equals my hypotenuse, which is called y this time, squared. 10 squared is 100. 15 squared, 225. So 100 plus 225 equals y squared. Now I'm writing out every step of the calculation here. As you get comfortable with this process, you might find that you're writing out less of it or just doing more of it on your calculator. That's totally fine. But I would definitely recommend writing out all of the steps at the beginning, just because it helps cement that process in your brain, helps make sure that you are not forgetting anything or making any mistakes. It also means that later you can go back to your notes and you can remind yourself of the steps that you were taking to solve these problems. All right, so next we've got 100 plus 225 is 325, which equals y squared. And our final step, you guessed it, is going to be to take that square root. So y equals the square root of 325. So y is I get 18.02. So if I round that, it's going to round to the nearest tenth. It'll be 18.0. 18.02 will round to 18.0. So y is equal to 18.0 inches. All right, on to number 3. So if we look at number 3, it's a little bit different. In number 3, we know one of the legs, we know the hypotenuse, and we're missing one of the legs here. So a slightly different setup. We're not solving for the longest side here. We're not solving for the hypotenuse. We're solving for one of the shorter sides. So I'm still going to start the same way. I'm just going to fill in the information I know. I'm going to call A. That'll stay the same. So A squared, we don't know what that leg is yet. That's our missing piece. And then B squared, that's going to be 12 squared equals 13 squared. So equals the hypotenuse squared. I'm going to do the same thing. I'm going to go through, evaluate those exponents. So 12 squared is 144. And 13 squared is 169. Okay, so now we run into where this process is going to be ever so slightly different from our more straightforward problems where we're just solving for the hypotenuse. So now we have this mystery amount here, A squared, plus 144 equals 169. So we need to figure out what this mystery amount is. If we have something plus 144 that equals 169, the way we can figure out that something is with subtraction. So A squared is going to be equal to 169 minus 144. So this is the really the only difference between this problem and the other right triangle problems that we've done so far. Instead of adding the two squares, we're going to be subtracting the two squares that we know. So 169 minus 144 is 25. So we get A squared is equal to 125, no, not 125, just 25. And so my final step is the same thing, is to take that square root of 25, which is 5. So we've discovered that A is equal to 5 kilometers. And we don't need to worry about doing any rounding here because we didn't have any decimal places. Okay, on to number 4. So when we look at number 4, we see that it's actually a similar situation to number 3. Number 4, we are told the hypotenuse and one leg, and we're solving for the second leg. That means that instead of adding our squares together, we're going to be subtracting them. So I'm actually going to go ahead and set up my problem to show that subtraction just right from the start. It'll just be a little less writing for me. So I know that my missing leg squared is going to be equal to my hypotenuse squared minus my other leg squared. Right, that's just what we did in number 3. We ended up saying that our missing leg squared was equal to our hypotenuse squared minus our leg squared. Okay, so 18 squared, that is 324. Try and squeeze all this in here. 324. And 12.25 squared is 150. 150.0625. So 150.0625. And in general, I would try not to round in the middle of a problem if you can help it. Of course, if you're getting an answer that's got like 8 decimal places or something like that, like you really don't need 8 decimal places, but if you've just got a few decimal places after the decimal point, I would keep those decimal places until the end of the problem, just so that you're not making too many changes to your numbers in the middle of the problem. In general, it's good practice to wait until the end of the problem to round. Okay, so z squared equals 324 minus 150.0625. So now I'm going to go ahead and subtract. And I'm going to have to jump down here so I got some space. I get that z squared is equal to 173.9375. And then my last step is going to be to take that square root. So the square root of 173.9375. And we get 13.18. So when I round that to the nearest tenth, it's going to round to 13.2. So our final answer is z is equal, or approximately equal since we rounded, to 13.2 feet. So, in general, when you're using your a squared plus b squared equals c squared formula, if you're solving for the hypotenuse, you're going to be squaring the numbers and then adding and then taking the square root. If you're solving for one of the legs, you're going to be squaring the numbers and then subtracting and then taking the square root. Okay, so we're going to finish up this lesson with 3 practice problems. These problems are intended to be more similar to the types of problems you might encounter on the GED test that would require you to use the Pythagorean theorem. So number 1 says, what is the distance between points L and M? What is the distance between points L and M? Now, when you first look at a problem like this, it might not be obvious that this is a problem involving the Pythagorean theorem, but it might jump out at you if you've been paying close attention to our discussions we've had about slope, right? So when we've talked about slope of a line, or when we connect 2 points, we think about the change horizontally. So we have this horizontal line. Just imagine that's a nice straight line. And then we have this vertical change that happens, this vertical line. So I've just created a nice right angle here. I've created 2 legs of a right triangle. So I've got a line going straight from L to M, or I can take this sort of roundabout route. I can go over and then up. And so I've created a right triangle, and I can use this right triangle to help me find this missing side, this side that's connecting point L and point M. So what I need to do now is I need to figure out the measurements of the 2 legs of this triangle. So I can use my grid to do that. I'm going to count how many spaces this line covers. So I'm going to start with the horizontal line here. So this line is 1, 2, 3, 4, 5, 6 spaces. You could see if you're paying attention to the x-axis here, the line is going from -4 to 2. So that's a span of 6. Okay, and then this other leg here, this vertical leg, is going from -3 up to +1. It's going up 1, 2, 3, 4 spaces. Okay, so now I've got my right triangle and I know the measurement of the two legs. So now I can solve for the hypotenuse. I can find the distance between points L and M. So I'm gonna use my formula, a squared plus b squared equals c squared. So again, I'm calling that line between L and M, I'm calling that line C. So 6 squared plus 4 squared equals c squared. That means 36 plus 16 equals c squared. And what is 36 plus 16? So 36 plus 16 is 52. 52 equals c squared. But we don't want to know c squared, we want to know c. So our last step is to take that square root. Square root of 52. Square root of 52 is equal to 7.211102551. Nice long decimal there. I'm going to round this to the nearest tenth. The question didn't include any directions about how to round it, so I'm just going to make a decision. I'm going to round it to the nearest tenth. So we'll say that the distance is approximately 7.2 units. And I can do a little common sense double check here, right? We know that our hypotenuse is always the longest side of the triangle. And so when you do your calculations, that number should come out a little bit larger than either of your two legs. And that's true in this case, right? We know that our hypotenuse is 7.2, just a little bit longer than either of our two legs. All right. Let's try the second practice problem here. So number 2, a river is 150 feet wide. Mara is swimming across the river. The current pushes her 25 feet downriver from where she started. How many feet did she actually swim? So I've got a little picture that I drew here of this situation, right? If there was no current in this river and she was able to just swim straight across, that would be 150 feet. So straight across this river is 150 feet, but she got pushed a little bit as she was swimming. The current pushed her downriver, so she ended up 25 feet down from where she started. So she actually swam a little bit longer than 150 feet. She swam this diagonal line here. So we are going to use the Pythagorean theorem to figure out the length of that line that she swam. So we've got our two legs, 150 feet squared, plus 25 feet squared, is going to equal the distance that she swam squared. I'm just going to call it m for Mara, so equals m squared. All right, now we do our calculations. So 150 squared equals 22,500. Nice big number. 22,500. We have 25 squared, I think is 625. Yep. So 25 squared is 625. And then when we add those together, we get 23,125. So the distance that she swam squared is equal to 23,125. Now, thankfully for poor Mara, that is not the final answer, right? She didn't have to swim 23,125 feet. We are not done yet. Our last step is to take the square root of that. I mean, you never know. She may have really been training and she might be ready to swim 23,125 feet is possible. But I think not today. Today she swam. Just made an error on my calculator. Let's get this in here. Square root of 23,125 is equal to 152.069. I'll just round that again to the nearest tenth to be consistent with what we've been doing so far. So 152.06, that'll round to 152.1 feet. So 152.1 feet. And hopefully that makes some sense to you. So if she meant to swim, that looks like 3. Make this a little less confusing here. So if she was trying to swim across the river, right, she was really trying to swim 150 feet, but she just got pushed. She got pushed just a little bit downriver, and so she ended up swimming just a little bit longer than she originally set out to swim. Okay, now let's take a look at our final question here. It says a 15-foot ladder is placed 5 feet away from a wall. How high up the wall does the ladder reach? So the ladder itself is 15 feet long. And then it's placed 5 feet away from the wall. So down here at the ground, we're setting it 5 feet away from the wall. So that is from here to here. So you'll notice we've got a nice right triangle that the ladder is making with the wall, right? The ladder is leaning up against the house, making this nice right triangle. So 15 feet is our hypotenuse and 5 feet is one of our legs. We are looking for this missing leg. We're looking for how high up it's reaching. Now, of course, if the ladder was like right up against the wall with no space at all, then the ladder could reach 15 feet up the wall, right? Because it's 15 feet tall. But the ladder is not right up against the wall. The bottom of the ladder has to be pulled out so it can rest safely against the wall. So if the bottom of the ladder is pulled out, the ladder is not going to be able to reach 15 feet up. It's going to be a little bit less. It's going to slide down a little bit as we pull it out. So let's start plugging in our information here. I'm going to say that we're missing a squared. And since we're solving for a leg, I'm going to jump straight into setting it up as a subtraction problem, just like we did with those other examples. So it's going to be our missing leg squared is going to be equal to our hypotenuse square minus our other leg square. So 15 squared is 225. So our missing leg squared equals 225 minus 5 squared, which is 25. When we do that subtraction, 225 minus 25, we get 200. So our missing leg squared equals 200. And so our final step is to take the square root. And now don't be tempted to just do some regular old division here, right? We're not saying like 200 divided by 2 or anything like that. We're taking the square root. So the square root of 200, I get 14.1421, blah, 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 blah. So let's say we round that to the nearest tenth. We're going to say that that missing leg is approximately 14.1. So the ladder is reaching about 14.1 feet up the wall. And that's our final answer. Okay, so if you've made it to the end of this lesson, congratulations, nice work. I wanted to give a little overview of your assignments and things that you have to do for this week. So the first thing that is posted, if you look on our Google Classroom, you've got an intro post at the top of the list for this week. So that just goes over like the schedule for this week and the topic and all that good stuff, the link to our Zoom meetings. But then the second thing that's posted on the Google Classroom for this week is the vocabulary list and online learning links. So the vocabulary list and online learning links. The vocabulary list, what I did was I took our geometry vocabulary list that we've already been using, and I just added a few important terms that we're using this week. So if you've been studying your vocabulary, a lot of those words should look very familiar to you. I just added, I think, about 8 to 10 words in there. So things like theorem and right triangle, that kind of stuff. So make sure you go in and click the link to that vocabulary list and work on those flashcards. And then I've also got the online learning links. So those are just links to a few videos that give extra explanation and examples around the Pythagorean theorem, as well as exponents and roots. Okay, and then on Monday, I also posted the problem of the day. So you should give that a try. On Tuesday is going to be the vocabulary quiz. And then Wednesday is Worksheet Wednesday. So that'll be 10 problems for you to solve relating again to this lesson. So all of those questions are about using the Pythagorean theorem. And then on Thursday, there's going to be a study skills post that goes up on the Google Classroom. This is something new I'm starting this week. We'll see how it goes, but I just wanted to give you an opportunity, if you would like, to learn a little bit more about different strategies that you can use to improve your studying. Studying is, it's not easy. It's something that you can practice to get better at. And it's not just something that like you magically know how to do with no guidance or help at all. So I'm going to be posting some stuff that I hope is helpful, making a little video that you can watch. It's not required, but if you've ever found yourself feeling a little lost or frustrated when it comes to learning this material or studying for your GED, I highly recommend checking out that study skills post that's up on the Google Classroom. And then finally, we are wrapping up the week with a second problem of the day that goes up on Friday. So that is your to-do list for this week. As always, I am contactable in various ways. So you can always send me an email, you can send me a remind message, or you can give me a call. And I hope to be talking to all of you very soon. Take care.